In this video, I'm going to teach you how to analyze position time graphs. Now, I want you to ask yourself 4 questions when analyzing any of these motion time graphs. Question 1, what is the significance of the slope? Question 2, what is the significance of the area under the graph? Question 3, what is happening if the graph crosses the horizontal axis? And lastly, question 4, what does it mean if the graph is curving? Now we're going to be using the same position time graph that I taught you how to read in a previous video. This was created using a PHET simulation called the moving man. Let's start by answering question 1. What is the significance of slope for a position time graph? Now, recall to calculate the slope of this first segment, highlighted in yellow, which occurs between t equals 0 seconds and t equals 2 seconds, that we're going to use the rise over the run, that ratio. Also recall, for this particular position time graph, we're analyzing the horizontal motion of the moving man. So on the vertical axis, we have the moving man's horizontal position in units of meters. And on the horizontal axis, we have time in units of seconds. So our rise is calculated by taking the second position and subtracting the first position, and that being divided by the duration of time. Now on the graph, you can see position 1 to be 0, position 2, positive 5 meters, and of course the duration of time being 2 seconds. And this calculation will give you 2.5 meters per second. Look at your units here, meters per second. So it should be no surprise that the slope of a position time graph is actually going to give you the velocity. So in this first segment between 0 and 2 seconds, we see it has a positive slope. And that means the object is moving in the positive direction, which in this simulation was off to the right. Now let's look at the next segment between 2 and 4 seconds. For this section, it is very evident that the slope is 0, which means the object is stationary and not moving. Now, of course, we could calculate the slope to show that 5 minus 5 divided by 2 and having 0 in the numerator, we get 0 for the answer. And indeed, that confirms that the object is stationary and not moving when the slope is 0 on a position as a function of time graph. In the next segment, between 4 and 6 seconds, we see there's a negative slope. Well, the negative slope is showing that the object is moving in the negative direction, or off to the left in this case. We can calculate the slope for this segment paying attention to the signage for this vector quantity. And we get that the slope is equal to a negative 5 meters per second. So indeed, the moving man during this duration was moving off to the left at a constant velocity of negative 5 meters per second. Next question, what is the significance of the area under the graph? For this particular motion time graph, there's no relevant significance. So we will not be using this for analyzing position as a function of time graph. However, this will become very relevant for other motion time graphs in upcoming videos. So moving right on to question 3, what is happening if the graph crosses the horizontal axis? Well, in this case here, we can look at our final position being at 0, and our initial position of x naught is at 0 as well. So this is going to really depend on the starting position of the object, or x naught. In this example here, if we look at the displacement between x naught being at 0 meters and x final being also at 0 meters, it's very obvious that our change in position is 0. So in this case here, there is 0 displacement, but that is looking at our starting position being at 0 meters and our final position also being at 0 meters. The displacement is 0. Let's look at another example though. Here we can see that the object is moved off in the negative direction and it's gone past its starting position. So we have a negative displacement. So right here, when crossing the horizontal axis, the moving man at that instant is moving to the left, but moving past his starting position of x naught equals 0 meters. Now we can quantify this again by calculating the displacement or change in position. Notice I've included signage for this vector quantity. So the final position was negative 5 meters and the starting position was at 0 meters. So the change in position or displacement for the moving man is negative 5 meters or 5 meters to the left. Next, let's analyze this scenario where we're defining the starting position at positive 5 meters. So we're essentially going to calculate the displacement or change in position for the moving man for segment 3 of our position time graph between 4 and 6 seconds. If we were to look at the change in position for the moving man and quantifying it, paying attention to the signage, the final position is minus 5 meters. The initial position was positive 5 meters, and we're subtracting the initial position from the final position, which is going to give us a displacement of negative 10 meters or 10 meters to the left between time 4 seconds and 6 seconds. Now, our final question: what does it mean if the graph is curving when analyzing a position time graph? For position time graphs, it means the object is accelerating. Please remember that. Anytime there is curvature, the object is accelerating. Now let's take a look at this and get a visual. I am going to place a dot on a position of the curve and draw a tangent line to that dot. I'll repeat this. I am drawing a tangent line to a specific dot on this graph. Now let's do it again at another time. Let's draw a tangent line. Let's do it again. Let's draw a third tangent line. Now we're going to consider what's happening to these 3 tangent lines at these 3 instances on this position time graph. Well, you know, when we're finding the slope, the significance is that the slope is the velocity. In this case here, we're finding the slope of 3 different tangent lines at 3 different points on this graph at 3 different instances. So let's look at these. We see that each one of these slopes for each one of these tangent lines is changing. It's increasing over time. And when we have this changing velocity over time, by definition, as you learned in earlier videos, we have acceleration, which is our third vector quantity covered in College Board topics 1.1 and 1.2. So look at number 1. Look at that tangent line. The slope is 0. At number 2, the slope is now positive. At number 3, the slope is also positive, but notice it's steeper, i.e. it's greater in magnitude. So we have an increasing velocity as a function of time. And by definition, that is acceleration. Calculating a change in velocity, as we always do, we take the final vector quantity and we subtract the initial vector quantity from the final. And the slope of these tangent lines is giving you something called the instantaneous velocity. And I'll make a point to distinguish the term instantaneous velocity from average velocity. Instantaneous acceleration from average acceleration. We're going to be looking at that in upcoming videos. And it should make sense that because I'm looking at a specific point on this graph at a specific time and analyzing that tangent line to that point on the curve, that we are looking at instantaneous velocities at these 3 times. Let's look at 3 other times in this graph, because the graph is curving throughout this duration as well. So we want to understand and look at what does it mean if the graph is curving now between these 3 points on the graph. Let's start by looking at 1. At that instant, around 10.5 seconds, we have a positive slope. At t equals 2, or excuse me, not t equals 2, at position 2 on this graph, we still have a positive slope. Look at the tangent line drawn through this point on this curve. It is still positive. Then at number 3, we see that the slope is 0. And that's occurring just before 12 seconds. So what do we see between 1, 2, and 3? Between this time of 10.5 and 12 seconds, we see the velocity is decreasing. If the velocity is decreasing or changing as a function of time, then we again have acceleration. This acceleration is different though, isn't it? Because the moving man is slowing down during this 1.5 second time period. In other words, we have a negative acceleration occurring when compared to what we analyzed previously, where the velocity increased over time. In this case, the velocity is decreasing over time, which is indicative of a negative acceleration. Lastly, let's look at what's occurring between t equals 12 and 18 seconds, which is off the graph on the horizontal axis, but it does extend to 18. We see here that no matter where we find the slope, remember the slope is significant. The slope is a velocity. No matter where we find it during this 6-second duration, we get the same value, which means the velocity is not changing. And that means there's no acceleration at all. If we look at our final and initial quantities and we pay attention to signage, we have a negative slope throughout, which means we're taking a negative 1.25 and subtracting a negative 1.25. Well, we get a change in velocity of 0 meters per second. And that means that during this period, there is no acceleration. we have constant acceleration here. Velocity is not changing. I want to look at a few other aspects of this position time graph. First, I want to look at these 4 areas here. These cusps are areas of infinite acceleration, and that term is confusing, but let me go ahead and elucidate it for you. It means that the moving man is instantaneously changing direction, which means there's an instantaneous acceleration. And that's simply not possible. And in this course, I want to address some of these points, and we're going to talk about how it's not possible. For example, in this first cusp here, the moving man is moving to the right with a constant positive velocity, and then instantly stops at t equals 2 seconds. Well, there must be some sort of deceleration occurring during that point there. And the same holds true for these other cusps on this graph. And so to be more realistic here, there should be some sort of curvature occurring there, some tiny finite amount of acceleration occurring there. And so it's important for me to point this out. Now, position time graphs can also be used to represent one-dimensional vertical motion. And recall, we denote that with the symbol of y, and the arrow is also used to denote the fact that it is a vector quantity. And I'm going to teach you how to analyze the position time graphs looking at vertical position in an upcoming video and in class, but you'll be happy to know you're pretty much doing the exact same things that I've taught you for this horizontal motion. So in this video, we've looked at a number of College Board's learning objectives, mostly dealing with looking at graphical representations, but also being able now not only to read these graphs, but to analyze these graphs as well. And I'll see you guys in class.